Hello, today we'll be learning about power series, Taylor series, and different ways we can see a question with this subject on a test or on the AP test. So our first example is finding a power series for ln of 5 minus x. So first we have to identify that this is going to be an integration problem, and I created it such that the integral on the other side is equivalent. So we have the integral of -1 divided by 5 minus x. So how do we get into this format of 1 divided by 1 minus x, which is what we need? Well, in this case, it's simple. We just take out a -1/5, and we are left with 1 divided by 1 minus x over 5. Now, it's very important to keep whatever we take out inside the integral, as very often, if we take it outside, we'll yield the wrong answer, and that is one of the most common mistakes. So next, we create the power series, and we have x divided by 5 to the n, which is this x in here. And next step, we just get the -1 divided by 5 and put it inside the power series. So we can see the -1 here. And then 5 to the n, you add that 5, so it becomes 5 to the n plus 1. So now the tricky part, which is integration. So as you can see, we remain at n equals 0 to infinity. -1 and 5 to the n plus 1 remain the same. We add 1 to the power of x, so we get x to the n plus 1, and then we will divide by the power of x, which is in this case n plus 1. And then one of the most important yet simple things is the plus c. It's very often forgotten because often it is 0, but in this case, as we will see, it is not. So how do we find c? C is just found by plugging in x equals 0 to the original function. So we get ln of 5 minus 0 equals ln of 5, and that's c. Simple enough. So we get ln of 5 plus the sum from n equals 0 to infinity of -1, x to the n plus 1, divided by 5 to the n plus 1, and n plus 1 again on the bottom. The next problem we will be looking at is creating a Taylor series centered around a certain number a, in this case 2, for the function e to the -3x. So the first step in creating a Taylor series is taking the first, second, third, fourth, and however many derivatives you need to find the pattern. And then, when it's centered at a certain number, plugging in that a for x, and as we can see here, we found those numbers. So the first thing we must observe is that we're going to create a series in which we have n factorial on the bottom, and then x minus 2, x minus 2 squared, x minus 2 to the third, continuing in the same powers as the n's, which is why this one does not have anything, since it would be x minus 2 to the power of 0. And with the same power of n, we have the derivative, thus f to the nth derivative of a, and we will then simplify to get this. Here we must observe all the patterns in order to create the power series, or Taylor series in this case. The first thing we will observe is that it alternates from positive to negative, thus -1 to the n. Next we observe that it goes from 3 to 9 to 27 to 81, so it's 3 to the nth power. We always have, in this case, n factorial on the bottom, which can be seen here. E to the -6, which I put here as e to the 6th on the bottom. And then the final aspect is to have x minus a to the nth power. And if you'd like to check, you can plug in a few numbers beginning at n equals 0, going up all the way to infinity, and you will be continuing to expand into this power series. So now that we know how to write a power series in Taylor and Maclaurin series, we're going to look at the interval of convergence. So here you can see the series such that x minus 3 to the 2n plus 1 times -1 to the n, which we'll call it to be alternating. Then we have 2n plus 1 factorial on the bottom, and n plus 6. So for this, we're going to use the ratio test, since the root test would not work. So to reiterate, the ratio test is the limit as n approaches infinity of a of n plus 1 divided by a of n, and the absolute values are very important since that is a common mistake. Now we will do it such that every single n in a of n is replaced to a of n plus 1, and since we are dividing by a of n, it's going to be multiplying by the reciprocal of the original. You can check that here. Now we go on to simplifying. So x minus 3 to the 2n can be simplified with this x minus 3 to the 2n and crossed out. Negative 1 to the n and negative 1 to the n can be crossed out. And x minus 3 to the third power can be crossed out with x minus 3 to the first power, such that only x minus 3 squared is left on top. Now, another common mistake is 2n plus 1 factorial divided by 2n plus 3 factorial simplification. When we expand both factorials, the only thing that does not cancel out on the bottom will be a 2n plus 2 and a 2n plus 3 due to the difference between these two. Now, I separated n plus 6 over n plus 7 because they cannot be cancelled, but the limit as n approaches infinity of n plus 6 over n plus 7 is equal to 1, thus they can be ignored in the end. Now, we have the simplified version. The limit as n approaches infinity of x minus 3 squared, we have a negative on top, divided by 2n plus 3, 2n plus 2 on the bottom. Always absolute values until we stop. Now, we simplify that such that the absolute values take out that negative 1 and the rest stays the same. And the limit as n approaches infinity when there's only n's on the bottom will result in 0, which is less than 1. Now, if we remember correctly, the limit as n approaches infinity of a of n plus 1 over a of n in absolute values, when that equals 0, or specifically less than 1, for all x, thus, that means the radius of convergence is r equals infinity. But we're not done yet. This is another common mistake, is people will forget to do interval of convergence. Now, the interval of convergence is negative infinity to infinity in this case, due to the radius. So here we are going to learn how to write the 5th degree Taylor polynomial for sine of 2x at a equals pi. The key word here is polynomial, because very often they will say polynomial, but people will write the series, but that's not what they're looking for in this problem, and it makes our life easier. So we're going to do a very similar step to what we did when we were trying to find the series, taking the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, and even sixth derivative, which will be used in the next problem. Then, again, we plug in pi for a, and we see that every 2, we have a 0 value. Now, we're going to still keep them in mind when writing out our Taylor polynomial at first. So, again, we have n factorials on the bottom. We have nth power for x minus a, which is in this case x minus pi. And we have f to the nth derivative at a. So we can see that written out all the way here up to f to the 5th derivative of pi, x minus pi to the 5th power over 5 factorial. Now we're going to simplify, and we can see the zeros pop up here, here, and here. But the reason they're so important is because very often when people don't use them, they will not get the correct numbers for the 5th degree, since they will believe that that means 5 polynomials. But as we will see in the answer, that is not necessarily true. So we simplify, and we get 2x minus pi minus 8 divided by 6, x minus pi to the 3rd power, 32 divided by 120 times x minus pi to the 5th power. So here, what I was saying before is that even though it does not have 5 polynomials, it is of degree 5. So this is very important. The degree is the power of x minus a to that nth degree, such that you can see here, the 5th degree polynomial has a power of 5, where x minus a to the n is. Now, this is the last of the very important sections in the power series chapter, which is error bound, and if you want to be fancy, you can call it the Lagrange error bound of this 5th degree polynomial, which we used before in the previous problem, specifically on the interval from 3 pi over 4 to 7 pi over 6 to approximate a certain value on this interval. So the key to understanding an error bound is that we're trying to make this as big as possible so that we can say that the absolute value of the error is less than or equal to the Lagrange error. So first, a very important step is to determine z. So this is one of the trickiest parts in the Lagrange error. So we have f to the 6th derivative, because we're taking the 5th degree polynomial, so you always have the derivative 1 over the degree polynomial you have, which is negative 64 sine to the 2x, which I showed in the previous problem. Now we are going to plug in both endpoints, and we see that f to the sixth derivative of 3 pi over 4 yields a greater number than 7 pi over 6. And again, it's important to realize that since we're using absolute value, had this been a greater number, even if it's negative, we will take whatever is the greatest magnitude. Now, the reason for showing this specific case is that this is what you will use in almost every problem. But when there is sine or cosine involved, or trig, we can always assume that f to that derivative of z will be yielded from the highest number which the trig can give us, which in this case the interval led to that highest number, 64, but we can always assume that sine or cosine will yield that one value, so that, again, this can stay true. Now, so we said that z is 3 pi over 4, thus the sixth derivative at z is 64. Now I come back over here, and we have 64 times x, which is the z value we found, or if you're approximating a certain number, it would be that, minus a pi to the sixth power, again, because we're going 1 power above what we're trying to estimate for, divided by 6 factorial, again, and factorial. Now, we simplify this such that it becomes 64 pi to the 6th power divided by 4 to the 6th power, and 720 with that on the bottom. Again, the absolute value here did not make a difference, but it's very important to remember that it's absolute value error. So when you punch that into a calculator, you get 0.020863. Now, most often in Calc, we can just tell that you do 3 decimal points, but since we're trying to be as precise as possible, we will use more decimal points. I usually suggest around 6 or however many your calculator will give. Therefore, the absolute value error for using the 5th degree polynomial to approximate a number on the interval from 3 pi over 4 to 7 pi over 6 is, at the worst case scenario, 0.020863 off of the actual value. So this last problem is a culmination of what we've learned in this lesson, in which we take limits with the help of Taylor polynomials and expansion. This is one of the College Board's and our calculus teachers' favorite problems, which we see very often. So here we have the limit as x approaches 0 of arctan, or tan inverse of 4x squared, minus 4x squared, divided by x to the 6th power. The first thing we have to do is expand tan inverse of 4x squared, which I've shown before in this lesson, in which it expands to 4x squared minus 4 to the 3rd, x to the 6th, divided by 3. The bottom goes up by 2 every time, as you can see. The powers of 4 go up by 2 every time, and the powers of x go up by 4 every time, and this continues to n equals infinity. Now we have the limit as x approaches 0 of this polynomial, which we expanded before. This one you can expand further if you'd like, but it is not necessary. Minus 4x squared, same as before, all divided by x to the 6th. So we just changed tan inverse of 4x squared into these set of polynomials. Now we're going to simplify, and negative 4x squared plus 4x squared will cancel out, and we have nothing left, we have 0. Then we are going to have to divide everything by x to the 6th. So we have negative 4 to the 3rd power, x to the 6th, divided by 3 divided by x to the 6th. So these x to the 6th will cancel out. And then these, I've already divided x to the 6th, and as you can see, they still have x's. So, as we take the limit as x approaches 0, the only one which will not turn to 0, and all of the following, since x is just increasing, will also go to 0, will be this first term here, which equals negative 4 to the 3rd power divided by 3. Just to simplify that out, you get negative 64 divided by 3. And here you've seen a great problem to show that you really know how to expand polynomials and take limits and simplify.